Welcome back to The Drowsy Astronaut, where tonight we explore every type of star that shines in the universe. And we will move through them slowly, one category at a time, letting the wonder settle gently. This is a journey through light and heat, through objects so distant they appear as points. Yet each one is a world unto itself, a sphere of fusion fire that burns for millions or even trillions of years. You can relax, work along, or drift towards sleep while I describe these stellar types. Or, if you're still awake for a moment, tell me where you're listening from, which country, which sky, and what time it is for you right now. And if these quiet journeys help you rest, consider subscribing and tapping that little bell so you don't miss our next voyage. Tonight, we begin with the question of what makes a star, and then we will walk through every category from the coolest brown dwarfs to the hottest blue giants. By the end, you will understand the rainbow of stars that fills the night sky, knowing why some glow red, others shine blue, and how each type lives and dies across cosmic time. The journey covers billions of years of stellar evolution, but we move through it gently, letting each concept rest before moving to the next, building understanding layer by layer. So let us begin with the basics, with what defines a star and separates it from planets, asteroids, and the cold, empty dark. A star is fundamentally a sphere of gas held together by its own gravity. And at its core, hydrogen atoms fuse into helium, releasing energy that makes the star shine. This fusion process is what separates stars from planets, because planets may be large and may have heat, but they do not generate energy through nuclear fusion in their cores. The balance between gravity pulling inward and fusion pressure pushing outward creates stability. And this balance can last for millions, billions, or even trillions of years depending on the star's mass. When fusion begins in a collapsing cloud of gas, a star is born, and it will shine until its fuel is exhausted. A journey we will explore across many types tonight. Stars come in an enormous range of sizes, temperatures, colors, and lifespans. And mass is the primary factor that determines all of a star's other properties. A star with low mass burns slowly and lives for trillions of years, while a massive star burns fiercely and dies in just millions, a brief candle compared to its smaller siblings. Temperature determines color, with cool stars glowing red and hot stars shining blue. And this relationship is consistent, allowing astronomers to understand stars by analyzing their light. Our Sun sits in the middle of this range, a yellow star of average mass and average temperature, neither the coolest nor the hottest, a perfect baseline for comparison. The life of a star follows a predictable pattern based on its mass, and it begins in a cloud of gas, collapses under gravity, ignites fusion, and enters a stable phase called the main sequence. Most of a star's life is spent on the main sequence, burning hydrogen steadily in its core, maintaining balance between gravity and pressure for billions of years. Eventually, the hydrogen fuel runs out and the star begins to change, entering phases of expansion, contraction, and sometimes violent death, depending on how massive it was to begin with. The smallest stars will live longer than the current age of the universe, while the largest stars explode as supernovae after just a few million years, and their remnants become exotic objects. Picture yourself floating in space far from Earth, where the night is absolute, and around you in every direction shine stars of different colors: red, orange, yellow, white, blue. Each color represents a different temperature, a different mass, a different stage of life, and a different destiny waiting billions of years ahead. Some of these stars are barely larger than Jupiter, while others are so vast they would engulf the orbit of Mars if placed where our Sun sits. Tonight we will meet them all, one type at a time, and by the end you will understand the diversity hidden in those points of light above. Stars create the elements that make up everything around us, and in their cores, fusion forges carbon, nitrogen, oxygen, iron, and all the atoms that form planets and life. When massive stars die, they explode and scatter these elements into space, and new stars and planets form from that enriched material, continuing the cycle of creation. You are made of stardust, literally, because every atom in your body except hydrogen was forged inside a star that died before the sun was born. This connection makes studying stars deeply personal, because understanding them means understanding our own origins across billions of years of cosmic history. The classification of stars uses a system based on temperature and spectral features, and astronomers organize stars into types labeled O, B, A, F, G, K, and M, from hottest to coolest. This sequence is remembered by the phrase, "Oh, be a fine girl, kiss me," though modern astronomy has added brown dwarfs below M, extending the range to even cooler objects. Each letter represents a range of temperatures and colors, and within each type, numbers from 0 to 9 provide finer gradations, so our Sun is classified as G2, a specific shade of yellow. This system helps astronomers communicate precisely about stars, and tonight we will walk through these categories from the coolest to the hottest, understanding what makes each type unique. We will also explore stars beyond the main sequence, including giants, supergiants, white dwarfs, and neutron stars, each representing different stages or outcomes in stellar evolution. Some stars expand to enormous sizes, becoming red giants, while others collapse into dense remnants smaller than Earth but containing the mass of the Sun. The universe contains billions of galaxies, each with billions of stars, and every one of those stars fits somewhere in the classification system we will explore tonight. By understanding the types, you understand the architecture of the cosmos and the patterns that govern how stars are born, live, and die across all of space and time. So, take a slow breath, settle into comfort, and let us begin our journey through the stellar zoo, starting with the coolest and faintest objects that barely qualify as stars. We will move gently, one type at a time, and if you drift towards sleep along the way, that is perfectly fine, because the stars will still be there when you wake. And there is no rush in learning about objects that burn for billions of years. Let us begin. Brown dwarfs are the first category we encounter, and they occupy a strange boundary between planets and stars, massive enough to glow from their own heat, but not massive enough to sustain hydrogen fusion. These objects form like stars, collapsing from clouds of gas and dust, but they never accumulate enough mass to ignite the fusion reactions that power true stars. A brown dwarf typically has a mass between 13 and 80 times that of Jupiter, which sounds enormous compared to planets, but is far too small to become a star like the Sun. Without sustained fusion, brown dwarfs simply radiate away their birth heat over time, slowly cooling and dimming across billions of years until they become cold, dark objects invisible to most telescopes. The temperature of a brown dwarf ranges from about 300 to 2,500 Kelvin, and the coolest ones are actually colder than some planetary atmospheres, barely glowing in infrared light. Their color, if you could see it, would range from dull red to almost invisible. And most brown dwarfs emit most of their light in wavelengths our eyes cannot detect. These objects are difficult to find because they are so dim, and astronomers discovered the first confirmed brown dwarf only in 1995, despite decades of searching. Now we know brown dwarfs are probably quite common, perhaps outnumbering true stars in some regions of the galaxy, a hidden population of failed stars drifting through the dark. Brown dwarfs do experience one brief phase of fusion early in their lives, when they burn deuterium, a heavier isotope of hydrogen that ignites at lower temperatures than regular hydrogen. This deuterium fusion lasts only a few million years, and once the deuterium is exhausted, the brown dwarf has no further fusion reactions, just the slow radiation of internal heat. Some of the most massive brown dwarfs, near 80 Jupiter masses, might sustain lithium fusion as well, but this too is brief and provides little energy compared to the hydrogen fusion that powers real stars. After these early phases, a brown dwarf simply cools, its surface temperature dropping slowly, its brightness fading until it becomes a dark, cold remnant wandering through space. The atmospheres of brown dwarfs are fascinating and complex, containing clouds of iron droplets, silicate dust, and in the coolest ones, even water vapor and methane. These clouds create weather systems unlike anything on planets, with storms of molten iron raining down through layers of gas, and winds that circle the object in patterns shaped by its rapid rotation. Some brown dwarfs rotate incredibly fast, completing a full spin in just a few hours, and this rotation creates strong magnetic fields that produce radio emissions and auroras. Observing these features helps astronomers understand the boundary between planets and stars, and how objects form and evolve in the mass range between these two categories. Picture standing on a hypothetical planet orbiting a brown dwarf, where the sky would glow faintly red or perhaps not at all, depending on the brown dwarf's temperature. The light would be dim, like deep twilight on Earth, and you would feel warmth from the brown dwarf, but far less than from even the coolest red dwarf star. The night would last forever if you were tidally locked with the brown dwarf hanging motionless in the sky, and the stars beyond would be incredibly bright because no bright central star washes them out. This would be a quiet, cold world, lit by a failed star that glows like an ember, neither planet nor star, but something in between. Astronomers continue discovering brown dwarfs throughout the galaxy, and each new find teaches us more about the spectrum of objects that form from collapsing gas clouds. Some brown dwarfs orbit other stars as companions, while others drift alone through interstellar space, solitary and dark, detected only by their faint infrared glow. The coolest brown dwarf ever found has a temperature around 250 Kelvin, colder than Earth's average temperature, an object that challenges our definitions of star versus planet. These discoveries blur the lines between categories, reminding us that nature does not always fit neatly into the boxes we create. Red dwarfs are the most common type of star in the universe, and astronomers estimate that 70 to 80% of all stars are red dwarfs, an overwhelming majority. These stars are classified as M-type stars, with masses ranging from about 0.08 to 0.5 times the mass of the Sun, and temperatures between 2300 and 3800 Kelvin. Their color is deep red to orange red, and they are so dim that not a single red dwarf is visible to the naked eye from Earth, despite their vast numbers. The closest star to our Sun, Proxima Centauri, is a red dwarf located just 4.2 light-years away, yet you need a telescope to see it. Red dwarfs burn their hydrogen fuel incredibly slowly compared to larger stars, and this efficiency means they can live for trillions of years, far longer than the current age of the universe. The universe is only 13.8 billion years old, so every red dwarf ever born is still on the main sequence, still burning hydrogen, and none has yet reached the end of its life. In the far future, trillions of years from now, red dwarfs will be the last stars shining in a universe that has grown dark and cold, lonely lighthouses in an empty cosmos. This incredible longevity makes red dwarfs fascinating for thinking about the long-term future of the universe and where life might persist across deep time. The small size of red dwarfs means they are fully convective, which means hot gas from the core circulates throughout the entire star, mixing thoroughly and bringing fresh hydrogen fuel to the core. This convection allows red dwarfs to burn almost all their hydrogen, not just the core supply, which contributes to their extraordinary lifespans. By contrast, more massive stars like the Sun have radiative cores where energy moves outward through photons, and much of their hydrogen never reaches the core and remains unburned. Red dwarfs are therefore incredibly efficient fusion reactors, squeezing every possible joule of energy from their fuel over spans of time we can barely comprehend. Despite their efficiency, red dwarfs are not calm and steady like larger stars, and they experience violent stellar flares, sudden eruptions of energy that can increase their brightness by several times. These flares are caused by magnetic activity, similar to solar flares on the Sun, but proportionally much stronger. And they release intense bursts of ultraviolet radiation and X-rays that bathe nearby planets. For planets orbiting in the habitable zone of a red dwarf, where liquid water could exist, these flares pose serious challenges for life, potentially stripping away atmospheres and sterilizing surfaces. The habitable zone is also much closer to the star, which means planets there are likely tidally locked, with one side always facing the star and the other in eternal darkness. Tidally locked planets have one hemisphere in perpetual day and the other in permanent night, and this configuration creates extreme temperature differences that drive powerful winds and unusual weather patterns. Life on such a world, if it exists, would need to adapt to either the scorching day side, the frozen night side, or the terminator zone between them, where temperatures might be more moderate. Some scientists argue that red dwarf planets could still support life despite these challenges, because thick atmospheres could redistribute heat, and organisms might evolve to withstand radiation and temperature extremes. Other researchers are more pessimistic, suggesting that flares and tidal locking make red dwarf planets hostile to life, at least life as we know it. Proxima Centauri hosts at least 2 known planets, including Proxima b, which orbits in the habitable zone. And this planet has been the subject of intense study and speculation about whether it could harbour life. Proxima b orbits its star every 11 days, extremely close compared to Earth's year-long orbit, and it likely presents the same face to the star always, locked in synchronous rotation. The star's flare activity means the planet is periodically bathed in intense radiation, but if it has a magnetic field and thick atmosphere, some regions might remain protected and potentially habitable. We do not yet know if Proxima b has an atmosphere, and answering that question is one of the goals of next-generation telescopes currently being designed and built. Red dwarfs are excellent targets for searching for exoplanets because their small size makes planetary transits easier to detect. And the close-in habitable zone means planets orbit quickly, allowing multiple observations. Astronomers have found hundreds of planets around red dwarfs, and many of these planets are rocky and located in or near the habitable zone where liquid water might exist. The sheer number of red dwarfs in the galaxy, combined with the high rate of planet occurrence, suggests that red dwarf planets are the most common potentially habitable worlds in the universe. If life is common and adaptable, red dwarf planets might host most of the life in the galaxy simply because they are so numerous. Picture yourself standing on a rocky planet orbiting a red dwarf star, where the sky glows a deep red and the landscape is bathed in dim crimson twilight that never brightens or fades. The star hangs motionless in the sky, neither rising nor setting. And the light is gentle, lacking the harsh brightness of our sun, creating a world of perpetual dusk. The air might be thick and warm, heated by the star's radiation and circulated by powerful winds that blow from the day side to the night side. And the stars beyond would be clearly visible even during the day. This would be an alien world, but not necessarily a lifeless one. And under that red sun, life might adapt in ways we have not yet imagined. Red dwarfs will dominate the universe's future, and long after the sun and all similar stars have died, red dwarfs will continue shining, islands of light in a darkening cosmos. In 1 trillion years, the universe will be colder and emptier, and the only stars remaining will be red dwarfs slowly burning through their vast reserves of hydrogen. Any civilizations that exist in that distant era will depend on red dwarfs for warmth and energy, and the galaxy will be a darker place lit only by these faint embers. But for now, red dwarfs are everywhere, the silent majority, and understanding them means understanding the most common type of star in the universe. Orange dwarfs are K-type stars, and they occupy a sweet spot between the dim, volatile red dwarfs and the shorter-lived sun-like stars, combining long lifespans with relative stability that might make them ideal for harboring life. These stars have masses between 0.5 and 0.8 times the Sun, and temperatures ranging from 3,800 to 5,200 Kelvin, giving them a warm orange color. Their lifespans range from 15 to 30 billion years, which is longer than the current age of the universe, but not as extraordinarily long as red dwarfs. This extended lifespan gives planets around orange dwarfs billions of extra years for life to evolve and develop complexity compared to planets around sun-like stars. Orange dwarfs are more stable than red dwarfs, with fewer and less intense stellar flares, and their habitable zones are farther out, reducing the likelihood of tidal locking for planets that might support life. This combination of stability and longevity makes orange dwarfs increasingly popular among astrobiologists, who argue that these stars might be the best places to search for complex life or even civilizations. A planet in the habitable zone of an orange dwarf would orbit every few weeks to months, receiving steady, warm light without the violent radiation outbursts that plague red dwarf planets. The conditions would be similar to Earth, but slightly cooler and redder. A comfortable environment where evolution would have enormous stretches of time to work. Alpha Centauri b is an orange dwarf and one of the closest stars to Earth, orbiting in a binary system with Alpha Centauri a sun-like star just 4.37 light-years away. This star is slightly smaller and cooler than the Sun, and while no planets have been confirmed around it yet, it is considered a prime candidate for hosting habitable worlds. Epsilon Eridani is another well-known orange dwarf, located about 10 light-years away, and it is surrounded by a debris disk that suggests planetary formation occurred or is still occurring. These nearby orange dwarfs are targets for future direct imaging missions, which hope to photograph planets orbiting them and analyze their atmospheres for signs of life. The habitable zone around an orange dwarf is closer than Earth's orbit, but farther than for red dwarfs, typically ranging from about 0.4 to 0.8 astronomical units, depending on the star's exact mass and temperature. Planets in this zone would receive enough warmth for liquid water, and they would orbit with periods measured in months, fast enough for seasonal changes if their orbits are slightly elliptical. Because the habitable zone is farther out than for red dwarfs, planets are less likely to become tidally locked, which means they could rotate normally with day-night cycles like Earth. This normal rotation might be important for maintaining magnetic fields, which protect atmospheres from stellar wind and create stable conditions for life to thrive. Orange dwarfs produce less ultraviolet radiation than sun-like stars, which reduces the risk of surface sterilization on nearby planets, but might also slow the chemistry that leads to life's origin. UV light can be both harmful and helpful, breaking molecules apart but also driving reactions that form complex organic compounds, and the balance matters for how life emerges. Planets around orange dwarfs would receive a softer radiation environment, which might favor the long-term survival of life once it starts, even if the origin process takes longer than around more energetic stars. This trade-off between radiation intensity and stability is one reason scientists debate which stellar type is truly best for life. The color of sunlight on a planet orbiting an orange dwarf would be noticeably different from Earth, with a warm orange hue that shifts the appearance of everything under that sky. Plants might evolve different pigments to capture the orange light efficiently, perhaps appearing black or dark purple instead of green, maximizing absorption across the shifted spectrum. The sky would be a deeper blue or perhaps tinted orange near the horizon, and sunsets would be spectacular, the sun appearing larger and oranger than our sun appears from Earth. Living under an orange star would feel familiar but subtly different, warm and comfortable, but with a color palette shifted toward longer wavelengths. Orange dwarfs represent about 12% of all stars in the galaxy, which is far less common than red dwarfs, but still amounts to billions of stars in the Milky Way alone. Their relative abundance, combined with their favorable characteristics, makes them statistically likely to host a large number of potentially habitable planets. If we ever make contact with another civilization, there is a reasonable chance they orbit an orange dwarf, a star that has given them billions of years to develop technology and culture. These Goldilocks stars, not too hot and not too cold, might be where most of the galaxy's life exists, quietly evolving under steady orange light. Picture yourself on a world orbiting an orange dwarf, where the sun rises in a sky that glows with warm amber tones, and the light feels gentle and golden, not the harsh white of our sun. The days are slightly longer or shorter than Earth's depending on the planet's rotation, but they follow a familiar rhythm, sunrise to sunset, not the eternal day of a tidally locked world. Forests here might be dark and lush, their leaves evolved to capture every photon of orange light, and the landscape would shimmer in hues we might find alien yet beautiful. This is a world where life has had immense time to flourish, and complexity might reach levels we have not yet imagined, all thanks to the steady light of a star that burns slow and long. Yellow dwarfs are G-type stars, and they include our own Sun, the star that makes life on Earth possible, with temperatures between 5,200 and 6,000 Kelvin and masses ranging from 0.8 to 1.2 solar masses. These stars emit light that appears white or yellowish-white to our eyes, though photographs often show the Sun as yellow because our atmosphere scatters blue light, leaving the longer wavelengths to reach us. Yellow dwarfs represent about 7% of all stars in the galaxy, which makes them less common than red dwarfs, orange dwarfs, or brown dwarfs, but still numbering in the billions across the Milky Way. Their lifespans average around 10 billion years on the main sequence, which is long enough for complex life to evolve, but short enough that these stars will eventually die, unlike the trillion-year lifespans of red dwarfs. Our Sun is about 4.6 billion years old, meaning it is roughly halfway through its main sequence lifetime, and it has been burning hydrogen in its core steadily for all that time, providing stable energy to Earth. The Sun formed from a collapsing cloud of gas and dust, enriched with elements from previous generations of stars that died before the solar system existed, and this enrichment made rocky planets and life possible. In about 5 billion more years, the Sun will exhaust its core hydrogen, and it will begin to expand into a red giant, growing so large it will likely engulf Mercury, Venus, and possibly Earth. But for now, the Sun is stable, steady, and remarkably constant, varying its output by less than 1% over decades, a reliability that has allowed Earth's climate to remain habitable. Yellow dwarfs, like the Sun, are bright enough to warm planets at comfortable distances, and the habitable zone around a Sun-like star typically lies between 0.9 and 1.5 astronomical units, roughly where Earth and Mars orbit. Earth sits at about 1 AU from the Sun, receiving just the right amount of energy for liquid water to exist on its surface, neither too hot nor too cold for life as we know it. This position in the habitable zone has remained stable for billions of years, allowing life to emerge, evolve, and diversify into the rich biosphere we see today. Mars orbits at the outer edge of the habitable zone, and while it is cold and dry now, evidence suggests it once had liquid water and might have been habitable billions of years ago. The Sun is currently in a phase called the main sequence, where it fuses hydrogen into helium in its core, and this process will continue steadily for another 5 billion years before the hydrogen runs out. When the core hydrogen is exhausted, the Sun's core will contract and heat up, while the outer layers expand and cool, transforming the Sun into a red giant that might extend beyond Earth's current orbit. During this red giant phase, the Sun will fuse helium into carbon and oxygen, but this phase will last only a few 100 million years, a brief finale compared to the billions of years on the main sequence. Eventually, the Sun will shed its outer layers in a planetary nebula, leaving behind a white dwarf, a hot, dense remnant about the size of Earth, but containing most of the Sun's original mass. Solar activity on yellow dwarfs includes sunspots, solar flares, and coronal mass ejections, phenomena driven by magnetic fields, and these events can affect planets, particularly their atmospheres and magnetic environments. Sunspots are cooler regions on the Sun's surface where magnetic fields are strong, and they appear dark because they are about 1,500 degrees cooler than the surrounding photosphere. The number of sunspots varies on an 11-year cycle, with solar maximum featuring many spots and frequent flares, followed by solar minimum when the Sun's surface appears relatively smooth and calm. Solar flares and coronal mass ejections can send charged particles toward Earth, creating auroras, affecting satellites, and occasionally disrupting power grids when the events are particularly strong. Yellow dwarfs are the stars we understand best because we live around one, and this familiarity makes them a natural baseline for comparison when studying other stellar types. The Sun's spectrum has been measured in extraordinary detail, revealing thousands of absorption lines that correspond to specific elements in its atmosphere, and this spectroscopy tells us the Sun's composition and temperature. By studying the Sun up close, astronomers developed techniques that now apply to distant stars, allowing us to determine their properties even from light years away by analyzing the light they emit. The Sun is an average star in many ways, and understanding it helps us understand stars in general, making it a crucial foundation for all of stellar astronomy. Picture standing on Earth and looking up at our familiar Sun, a yellow-white disk that warms your skin and illuminates the world, and knowing that this star is one of billions of similar stars scattered throughout the galaxy. The light reaching you has traveled 8 minutes from the Sun's surface, but the photons themselves were created in the core through fusion reactions and took thousands of years to random walk outward through dense plasma. By the time sunlight touches your face, it has journeyed from nuclear furnace to surface to space, crossing the void to reach Earth, a tiny fraction of the Sun's total output, yet enough to power all life here. This connection to our star is intimate and ancient, and every living thing on Earth depends on the Sun's steady burning, a relationship that has endured for billions of years. If you could visit a planet orbiting another yellow dwarf light years away, the experience would feel remarkably similar to Earth, at least in terms of the star's light and warmth. The sky would be the familiar blue, assuming an Earth-like atmosphere, and the Sun would appear as a bright disk, white or pale yellow, indistinguishable from our own Sun. Plants would likely be green, using chlorophyll or similar pigments to capture the same wavelengths of light, and the day-night cycle would feel familiar, neither too fast nor too slow. This is why yellow dwarfs are popular in science fiction, because they offer environments that feel comfortable and recognizable to us, familiar stars around which human-like life seems most plausible. Yellow dwarfs will eventually die, but their deaths are relatively gentle compared to massive stars, ending not in violent supernovae but in the quiet shedding of outer layers into space. The planetary nebulae they create are among the most beautiful objects in the universe, glowing shells of gas lit by the hot white dwarf at the center, visible for thousands of years before fading into darkness. These nebulae enrich interstellar space with heavy elements forged in the star's core, and future generations of stars will form from this material, continuing the cycle of stellar birth and death. Our Sun will follow this path, and in about 7 billion years, it will become a white dwarf surrounded by a fading nebula, a quiet end to a star that nurtured life for billions of years. White stars include F-type and A-type stars, which are hotter, brighter, and more massive than yellow dwarfs like the Sun, and they burn through their hydrogen fuel faster, living shorter but more luminous lives. F-type stars have masses between 1.2 and 1.6 solar masses, with temperatures ranging from 6,000 to 7,500 Kelvin, while A-type stars range from 1.6 to 2.5 solar masses and 7,500 to 10,000 Kelvin. Their color appears white or blue-white to observers, and they emit more ultraviolet radiation than cooler stars, which has implications for any planets that might orbit them. Lifespans for F-type stars range from 1 to 3 billion years. while A-type stars live only 500 million to 1 billion years, much shorter than the Sun's 10 billion year lifespan. Procyon is an F-type star located about 11 light-years from Earth, and it is visible in the night sky as one of the brightest stars, part of the Winter Triangle asterism. Procyon has a mass of about 1.5 times the Sun, and it is currently in the later stages of its main sequence lifetime, slowly transitioning toward the red giant phase. Sirius is an A-type star and the brightest star in Earth's night sky. Located just 8.6 light-years away, and its brilliance is due to both its proximity and its intrinsic luminosity. Sirius has a mass about twice the Sun's and shines with 25 times the Sun's luminosity, and it is accompanied by a white dwarf companion, Sirius B, the remnant of a star that has already completed its life. The habitable zone around white stars is farther out than for Sun-like stars due to their greater luminosity, but the zone also migrates outward as the star ages and brightens, which complicates long-term habitability. Planets that start in the habitable zone might become too hot as the star evolves, and planets initially too cold might only enter the habitable zone late in the star's lifetime, leaving limited time for life to emerge. The short lifespans of white stars pose the biggest challenge for habitability, because complex life on Earth took over 3 billion years to evolve, and white stars may not provide enough stable time. Simple life might arise around white stars, but intelligence and technological civilizations would be unlikely unless evolution proceeds much faster than it did on Earth. White stars rotate faster than cooler stars on average, with some A-type stars spinning so rapidly they complete a full rotation in just a few hours. This rapid rotation causes them to bulge at the equator, making them ablate rather than perfectly spherical, and it also generates strong magnetic fields and stellar activity. The fast rotation affects how light is emitted from different parts of the star's surface, with the poles appearing brighter and hotter than the equator due to a phenomenon called gravity darkening. Some white stars also exhibit unusual chemical abundances, with elements like strontium, chromium, or europium appearing stronger in their spectra than expected, creating what astronomers call chemically peculiar stars. Many white stars, particularly A-type stars, are surrounded by debris disks of dust and gas, which might be the remnants of planet formation or the result of cometary collisions in young planetary systems. Vega, one of the brightest stars in the northern sky, is an A-type star surrounded by a prominent debris disk detected through its infrared emission. This disk suggests that planets might exist around Vega, though none have been directly confirmed yet, and the system is relatively young, only a few 100 million years old. Studying debris disks around white stars helps astronomers understand planet formation and the early evolution of planetary systems, including how rocky planets might assemble from colliding debris. Picture standing on a hypothetical planet orbiting an F-type white star, where the Sun appears brilliant and white, noticeably brighter than our Sun, but not yet the harsh blue of hotter stars. The light would be intense, rich in ultraviolet radiation, and you would need strong protection against sunburn, though a thick atmosphere might filter out much of the harmful UV. The sky might appear a deeper, richer blue than Earth's due to increased Rayleigh scattering, and plants, if they evolved here, might have developed different pigments to handle the intense light and UV exposure. Days would pass with a familiar rhythm, and the star would provide ample warmth. But the knowledge that this sun will burn out in just 1 billion years might create urgency for any civilization that evolves here. White stars are often found in binary systems or multiple star systems, where they orbit alongside other stars, sometimes creating complex gravitational interactions that affect planetary orbits. Sirius, for example, is a binary system with Sirius A, the bright white star, and Sirius B, a white dwarf that orbits the primary star every 50 years. These binary systems can be stable for billions of years, and planets might orbit either one of the stars in close orbits or circle both stars in wider, circumbinary orbits. The dynamics of such systems create challenges for planet formation, but observations show that planets do exist in binary systems, sometimes in surprising configurations that theory is still working to explain. The transition from white stars to true blue giants represents a jump in mass and luminosity, moving from stars that live hundreds of millions of years to stars that burn out in just tens of millions. As we move up the temperature scale, stars become more extreme in every way: brighter, hotter, shorter-lived, and more violent in their deaths. White stars occupy a middle ground, impressive but not yet entering the realm of the truly massive, and they represent a transition zone in stellar evolution where hydrogen burning accelerates noticeably. Let us now move to the most massive and luminous stars, the blue giants, where stellar physics pushes toward extremes and stars live fast, die young, and go out in spectacular explosions. Blue giants are the massive stars of the universe, classified as B-type and O-type stars, and they represent the most luminous, hottest, and shortest-lived stars on the main sequence. B-type stars have masses between 2.5 and 16 solar masses, with temperatures ranging from 10,000 to 30,000 Kelvin, while O-type stars range from 16 to over 150 solar masses, and temperatures from 30,000 to 50,000 Kelvin or higher. Their color is blue or deep blue, and they emit most of their energy in ultraviolet wavelengths, so much so that what we see as visible light is only a small fraction of their total output. Lifespans for B-type stars range from 10 to 100 million years, while O-type stars live even shorter lives, as brief as a few million years before exhausting their fuel and dying in supernovae. These stars are rare, making up less than 1% of all stars in the galaxy, but their immense luminosity makes them visible across vast distances, and many of the brightest stars in our night sky are blue giants. Rigel, the bright blue star in the constellation Orion, is a B-type supergiant, located about 860 light-years away, yet shining as one of the brightest stars visible from Earth. Its luminosity is roughly 120,000 times that of the Sun, and if you replaced the Sun with Rigel, Earth would be vaporized instantly from the intense radiation. This immense power output comes from rapid fusion in the core, where hydrogen is consumed at a ferocious rate, burning through fuel that would last the Sun billions of years in just millions. Blue giants have powerful stellar winds, streams of charged particles blown off the star's surface at speeds of thousands of kilometers per second, and these winds carry away significant amounts of the star's mass over its lifetime. An O-type star might lose a significant fraction of its original mass through stellar winds, reshaping itself and enriching the surrounding space with heavy elements even before it explodes. These winds create bubbles and shock waves in the interstellar medium, clearing out regions around the star and sometimes triggering the formation of new stars in the compressed gas at the bubble's edge. The interaction between stellar winds and surrounding gas creates beautiful structures like the Rosette Nebula, where hot young stars have carved cavities in the molecular clouds from which they formed. The surface of a blue giant is turbulent and dynamic, with convection patterns and magnetic fields that generate activity far more intense than anything seen on the Sun, though the specific mechanisms differ because blue giants have different internal structures. Unlike cooler stars, blue giants have convective cores and radiative envelopes, meaning that mixing occurs in the center where fusion happens, but energy travels outward through the outer layers via photon transport rather than convection. This structure affects how the star ages and how elements are distributed within it, and it means blue giants evolve differently than stars like the Sun, with different paths through later stages of stellar evolution. When a blue giant exhausts its core hydrogen, it often expands into a supergiant, growing to enormous size while its core contracts and begins fusing heavier elements like helium, carbon, and eventually iron. Blue giants are typically found in young star clusters and stellar nurseries because they form recently and die quickly, never traveling far from their birthplaces before their lives end. The Pleiades star cluster contains several bright blue stars, young B-type stars that have been shining for only about 100 million years and will die long before the cluster disperses. Orion's belt contains 3 bright blue giants, Alnitak, Alnilam, and Mintaka, all part of the larger Orion OB1 association, a region of recent star formation containing thousands of young stars. These stellar nurseries glow brightly in infrared and visible light, illuminated by the intense radiation from the massive blue stars that have recently formed from the surrounding gas and dust. The radiation from blue giants is so intense it ionizes surrounding hydrogen gas, creating glowing regions called HII regions that can be seen across intergalactic distances. The Orion Nebula is an HII region illuminated primarily by 4 massive O-type stars in the trapezium cluster at its heart, and their ultraviolet radiation causes the nebula's gas to glow in characteristic pink and red hues. These regions are stellar nurseries, places where new stars are still forming from the collapsing gas, and the intense radiation from the most massive stars both illuminates the nebula and eventually destroys it by evaporating the remaining gas. This feedback process limits how many stars can form in a given region, because once the massive stars ignite, their radiation and winds blow away the raw material needed for further star formation. Picture standing on a planet orbiting a blue giant, though such a planet would be unlikely to exist or survive, because the intense radiation and short stellar lifetime create hostile conditions for planet formation and stability. The star would appear as a brilliant blue-white torch, so bright you could not look directly at it, even with heavy filters, and the light would be rich in ultraviolet that would sterilize any unprotected surface. The sky might glow with auroras constantly, as the powerful stellar wind interacts with any planetary magnetic field. And the heat would be intense, likely making any rocky planet too hot for liquid water unless it orbited far from the star. Such a world would be a place of extremes, and if any life existed there, it would need to shelter deep underground or beneath thick ice to survive the onslaught of radiation and heat. Blue giants die in spectacular supernovae, explosions so powerful they briefly outshine entire galaxies, and these explosions forge heavy elements and scatter them into space, enriching the cosmos with the building blocks of planets and life. When a massive star exhausts its fuel, the core collapses in less than a second, and the rebound creates a shockwave that tears the star apart, releasing more energy in a few weeks than the Sun will produce in its entire lifetime. The remnant left behind depends on the original mass, either a neutron star, an incredibly dense object made of neutrons, or a black hole, a region where gravity is so strong that not even light can escape. These remnants are exotic objects where physics reaches its limits, and studying them helps us understand matter and gravity under conditions impossible to recreate in any laboratory. Blue giants are the engines of galactic evolution, their deaths enriching the interstellar medium and triggering new generations of star formation. And their short lives mean the galaxy constantly cycles material through these massive stars. Without blue giants, the universe would be poorer in heavy elements, and planets like Earth, rich in iron, silicon, and other metals, might never have formed. The oxygen you breathe, the carbon in your body, the calcium in your bones, all were forged inside massive stars and scattered into space when those stars exploded, eventually becoming part of the solar system and Earth itself. Blue giants are brief but crucial, the cosmic forges that create complexity, and their spectacular lives and deaths shape the universe in profound ways. Giant stars represent a later stage in stellar evolution, when a star has exhausted the hydrogen fuel in its core and begins to expand dramatically, growing to tens or hundreds of times its original size. This phase occurs for stars across a wide range of masses, from low-mass stars like red dwarfs eventually becoming red giants, to massive stars briefly passing through a giant phase on their way to becoming supergiants. The most familiar giants are red giants, stars that have swollen and cooled, and they appear red or orange due to their lower surface temperatures, typically between 3000 and 5000 Kelvin. Our Sun will become a red giant in about 5 billion years, expanding to roughly the orbit of Earth or beyond, engulfing Mercury and Venus, and possibly consuming our planet as well. Red giants form when a star exhausts the hydrogen in its core, and fusion stops temporarily, causing the core to contract under gravity and heat up. This contraction releases gravitational energy that heats the layers surrounding the core, and hydrogen fusion begins in a shell around the inert helium core, producing even more energy than the star generated during its main sequence phase. The extra energy causes the outer layers to expand enormously, and as the surface area increases, the outer temperature drops, giving the star its red or orange color. Despite the lower surface temperature, red giants are often more luminous than they were on the main sequence, because their vastly increased surface area more than compensates for the cooler temperature. Arcturus is a red giant located about 37 light-years from Earth, and it is the brightest star in the northern celestial hemisphere, shining with an orange-red color visible to the naked eye. Arcturus has a mass similar to the Sun, but it has already left the main sequence and expanded to about 25 times the Sun's diameter, making it a mature red giant. Its luminosity is about 170 times that of the Sun, and if you replace the Sun with Arcturus, its surface would extend past the orbit of Venus, and Earth would orbit deep within the star's outer atmosphere. Another famous red giant is Aldebaran, the orange eye of Taurus the Bull, located about 65 light-years away and roughly 44 times larger than the Sun. The interiors of red giants are structured in layers, with an inert core of helium ash at the center, surrounded by a shell where hydrogen fuses into helium, and vast outer envelopes of tenuous gas that extend to the star's swollen surface. The helium core continues contracting and heating until eventually, if the star is massive enough, It reaches about 100 million Kelvin and helium fusion ignites, a process called the helium flash in lower mass stars. This helium flash is a sudden, brief runaway fusion event that occurs in less than a second, releasing enormous energy that stabilizes the core and prevents further collapse for a time. After the helium flash, the star settles into a new phase of stability, fusing helium into carbon and oxygen in the core, while hydrogen fusion continues in a surrounding shell. Red giants are known for their variability, with many pulsating in size and brightness over periods of months to years. And these pulsations are driven by instabilities in the outer layers where the star's structure oscillates. Some red giants, called mirror variables after the star mirror, vary in brightness by factors of hundreds, changing from easily visible to nearly invisible over cycles lasting about a year. These pulsations are not perfectly regular, and the stars can be unpredictable, adding to their mysterious character and making them targets for amateur astronomers who monitor their changing brightness. Eventually, red giants exhaust their helium fuel as well, and lower mass stars like the Sun do not have enough mass to fuse heavier elements, so their cores contract into white dwarfs while the outer layers drift away. These shed outer layers form planetary nebulae, beautiful glowing shells of gas illuminated by the hot white dwarf at the center. And despite the name, they have nothing to do with planets. The term is historical and misleading. The Ring Nebula and the Helix Nebula are famous examples, each showing the expelled outer layers of a red giant that has reached the end of its fusion life and become a white dwarf. These nebulae fade over thousands of years as the gas disperses, but while they last, they are among the most beautiful objects in the night sky, colorful and intricate, remnants of stars that once shone steadily. Blue giants also exist, though they are less common and represent a different evolutionary path, typically involving more massive stars that expand but remain hot due to their greater energy output. These stars might be in a brief transition phase between the main sequence and becoming supergiants, or they might be unusual objects with specific chemical compositions or rotation rates that affect their evolution. Some blue giants are actually stars that have merged with companions in binary systems, gaining extra mass and heat that give them unusual colors and luminosities compared to typical stars of their age. Stellar evolution is not always simple, and blue giants remind us that stars can take unexpected paths depending on their environment, mass, and history. Picture the Sun, 5 billion years from now, swollen into a red giant, its surface extending past Venus and perhaps engulfing Earth, though by then our planet will have been scorched and sterilized long before being consumed. The sky from Earth, if the planet survives, would be filled entirely by the Sun's bloated red surface, no longer a disk but a vast wall of glowing gas stretching across the entire sky. The heat would have long since boiled away the oceans, stripped the atmosphere, and Earth would be a molten or vaporized ruin orbiting within the outer layers of its dying star. This is the fate awaiting Earth, and while it lies billions of years in the future, it reminds us that nothing in the universe is permanent, not even the sun that has nurtured life for so long. Supergiant stars are among the largest and most luminous stars in the universe, with sizes measured in hundreds or even thousands of times the sun's diameter and luminosities millions of times greater. These stars have masses typically between 10 and 70 solar masses, though some supergiants might have started with even more mass and lost significant amounts through powerful stellar winds over their lifetimes. Supergiants come in different colors depending on their temperature, with red supergiants being the coolest and largest, and blue supergiants being hotter but typically smaller, though still enormous by normal stellar standards. Their lifespans are brief, just 10 to 50 million years from birth to death, and they end their lives in spectacular core collapse supernovae that outshine entire galaxies for weeks. Betelgeuse is perhaps the most famous red supergiant, located about 650 light-years away in the constellation Orion. And it is so large that if placed where the Sun is, its surface would extend past the orbit of Jupiter. Betelgeuse has a diameter roughly 1,000 times the Sun's. Though measurements vary because the star's surface is irregular and pulsating, making it difficult to define where the surface actually ends. Its luminosity is about 100,000 times the Sun's, and the star shines with a deep red color visible to the naked eye, marking the shoulder of the constellation Orion the Hunter. Betelgeuse is near the end of its life, and astronomers expect it to explode as a supernova within the next 100,000 years, possibly much sooner, though predicting the exact timing is impossible. Antares is another red supergiant located about 550 light-years away in the constellation Scorpius, and its name means rival of Mars because its red color and brightness resemble the planet Mars when they appear near each other in the sky. Antares is roughly 700 times the diameter of the Sun, and if placed at the center of our solar system, its surface would extend past the orbit of Mars, engulfing all the inner planets. Its luminosity is about 60,000 times the Sun's, and like Betelgeuse, it is nearing the end of its life and will eventually explode as a supernova, though again, the timing is uncertain. These stars are unstable, pulsating and losing mass through powerful winds, and their surfaces are complex, with convection cells larger than the entire Sun creating irregular brightness patterns. Uae Scuti is one of the largest known stars by radius, a red supergiant located about 9,500 light-years away, though distance measurements are uncertain, making its exact size difficult to determine precisely. Estimates suggest Uae Scuti has a radius roughly 1,700 times the Sun's, which would place its surface beyond the orbit of Saturn if it replaced the Sun at the center of our solar system. Its luminosity is about 340,000 times the Sun's, and the star is so large that its outer layers are extremely tenuous, barely denser than a laboratory vacuum, yet still glowing and radiating immense energy. Stars this large are rare and unstable, and Uae Scuti varies in brightness over periods of years, pulsating and shedding mass as it approaches the final stages of its evolution. Blue supergiants are less common than red supergiants, but equally impressive, hot and luminous stars that have either left the main sequence recently or are in transition phases between different evolutionary stages. Rigel, which we mentioned earlier, is a blue supergiant with a luminosity of about 120,000 times the Sun's, and a surface temperature around 11,000 Kelvin, giving it a brilliant blue-white color. These stars are less stable than main sequence stars, experiencing variability and mass loss, and they represent stars in the prime of their lives, burning fuel at prodigious rates before their inevitable supernovae. Some blue supergiants are thought to be stars that have lost their outer hydrogen envelopes, revealing hotter inner layers, while others might be younger stars still contracting toward the main sequence. Supergiants have complex internal structures with multiple shell-burning layers, where different elements fuse in concentric shells around an inert iron core in the most massive examples. In a massive supergiant nearing its death, the core consists of iron, surrounded by shells fusing silicon, oxygen, neon, carbon, helium, and hydrogen from innermost to outermost, an onion-like structure of different elements. Each shell burns for progressively shorter times as the star ascends to heavier elements, with silicon fusion lasting only days before the core becomes iron, the end of the line for fusion energy. Iron fusion consumes energy rather than releasing it, so once the core becomes iron, the star has run out of options and collapse is inevitable, leading to a core collapse supernova. The explosion of a supergiant is one of the most energetic events in the universe, releasing more energy in a few seconds than the star produced during its entire life. The core collapses to a neutron star or black hole in less than a second, and the rebound shockwave rips through the star's outer layers, heating them to billions of degrees and ejecting them into space at a significant fraction of light speed. For a few weeks, the supernova can outshine an entire galaxy, making it visible across millions of light years, a cosmic beacon announcing the death of a massive star. The remnant, whether neutron star or black hole, is an exotic object where physics reaches extremes, and the ejected material enriches the galaxy with heavy elements forged in the explosion. Supergiants are engines of chemical enrichment, producing and distributing most of the heavy elements found in the universe, and without them, the cosmos would lack the diversity of atoms needed to form complex structures like planets and life. Elements heavier than iron are primarily created in supernova explosions, through rapid neutron capture processes that occur in the extreme conditions of the collapsing core and explosion. Gold, silver, platinum, uranium, and most other heavy elements owe their existence to supernovae, and the gold in jewelry or electronics was forged in the death throes of massive stars billions of years ago. Every supergiant that explodes enriches a portion of the galaxy, and over billions of years, successive generations of stars have built up the inventory of elements we see today. Picture watching a supergiant from a safe distance, billions of kilometers away, where the star appears as an enormous glowing sphere, dwarfing anything in our solar system, dominating the sky. Its light would be so intense that even at vast distances, it would cast shadows and provide warmth, a miniature sun that could illuminate worlds far beyond what our sun can reach. The color would depend on the type, deep red for a red supergiant or brilliant blue-white for a blue supergiant, and watching it would be both beautiful and terrifying, knowing the star's immense power and instability. When it finally explodes, the light would arrive suddenly, brightening to rival the full moon or even the sun for a brief time, a spectacle that would be visible across the galaxy, witnessed by anyone looking in that direction. Dying stars leave behind remnants that are among the strangest objects in the universe, and these remnants include white dwarfs, neutron stars, and black holes, each representing different outcomes depending on the original star's mass. White dwarfs are the remnants of low to medium mass stars, left behind when red giants shed their outer layers and exposed the hot core, an Earth-sized sphere containing about half to one solar mass. Neutron stars form from more massive stars that explode as supernovae, and the core collapses to a city-sized object made almost entirely of neutrons, with densities so extreme that a teaspoon of neutron star material would weigh billions of tons. Black holes form from the most massive stars, where the core collapse continues past the neutron star stage, and gravity becomes so strong that nothing, not even light, can escape from within the event horizon. White dwarfs are incredibly dense, with the mass of the sun compressed into a sphere about the size of Earth, and they have no ongoing fusion reactions, simply radiating away stored heat over billions of years. The temperature of a newly formed white dwarf can exceed 100,000 Kelvin, making it extremely hot and luminous despite its small size, but over time it cools and dims, eventually becoming a cold, dark black dwarf in the far future. However, the universe is not old enough for any white dwarfs to have cooled to the black dwarf stage, and even the oldest white dwarfs still glow faintly, remnants from stars that died billions of years ago. White dwarfs are supported against further collapse by electron degeneracy pressure, a quantum mechanical effect where electrons resist being pushed closer together, preventing the star from shrinking further under its own gravity. Sirius B is a famous white dwarf, the companion to Sirius, the brightest star in Earth's night sky, and it orbits the much brighter Sirius A every 50 years at a distance similar to the distance between the Sun and Uranus. Sirius B has a mass close to the Sun's, but its diameter is only about 12,000 kilometers, roughly the size of Earth, making it one of the nearest white dwarfs for study. The density is extraordinary, about 1 million times that of water, meaning a sugar cube-sized piece of Sirius B would weigh about a ton on Earth, far denser than any normal material. White dwarfs like Sirius B gradually fade over time, but they persist for trillions of years, far longer than most other stellar remnants, quiet ghosts of stars that once burned brightly. Neutron stars represent an even more extreme state of matter, formed when the core of a massive star collapses during a supernova and protons and electrons are forced together to create neutrons. The resulting object is typically about 20 kilometers in diameter, but contains 1.4 to 2 times the mass of the Sun, making it unimaginably dense, far denser than even white dwarfs. A teaspoon of neutron star material would weigh about 6 billion tons, and the gravity at the surface is so strong that if you dropped an object from 1 meter high, it would hit the surface at a significant fraction of light speed. The surface of a neutron star is thought to be a crystalline crust of iron nuclei, beneath which lies a superfluid interior of neutrons, a state of matter that cannot exist anywhere except in these extreme conditions. Pulsars are rapidly rotating neutron stars that emit beams of radiation from their magnetic poles, and as the star spins, these beams sweep across space like a lighthouse, creating pulses of radio waves or light that we detect as rhythmic signals. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, and the signal was so regular, pulsing every 1.33 seconds, that it was briefly considered a possible signal from an alien civilization. We now know of thousands of pulsars, with rotation periods ranging from milliseconds to seconds, and the fastest ones, millisecond pulsars, spin hundreds of times per second, their surfaces moving at a significant fraction of light speed. Pulsars slow down over time as they lose energy, and eventually they spin too slowly to generate detectable pulses, becoming quiet neutron stars that are difficult to observe without special techniques. Magnetars are neutron stars with extraordinarily powerful magnetic fields, 1,000 times stronger than typical neutron stars, and these fields can generate violent outbursts of X-rays and gamma rays that are detectable across the galaxy. The magnetic fields of magnetars are so strong they distort the neutron star's crust, causing starquakes that release enormous bursts of energy, briefly making the magnetar one of the brightest objects in the sky at certain wavelengths. These outbursts can affect Earth's upper atmosphere when they occur in relatively nearby magnetars, ionizing layers of the ionosphere and demonstrating the power of these distant objects. Magnetars are thought to form when massive stars with strong magnetic fields collapse, and the magnetic field is compressed and amplified to extraordinary strengths as the core shrinks to neutron star size. Black holes are regions of space-time where gravity has become so strong that nothing can escape. not even light once it crosses the boundary called the event horizon. They form when the core of a very massive star collapses, and nothing, not even neutron degeneracy pressure, can stop the collapse, and the core continues shrinking until it becomes a singularity, a point of infinite density. The event horizon is not a physical surface but a boundary in space, and anything that crosses it is doomed to fall toward the singularity, with no possible escape even in principle, regardless of how much energy it has. Black holes come in different sizes, stellar mass black holes from collapsed stars, and supermassive black holes at the centers of galaxies, millions or billions of times the mass of the Sun. We have detected black holes through their gravitational effects, by watching stars orbit invisible companions, by detecting gravitational waves when black holes merge, and by imaging the shadow they cast against glowing gas. The image from the Event Horizon Telescope showed us the shadow of a supermassive black hole, a dark circle surrounded by a bright ring of light, proving that black holes exist and behave as Einstein's equations predicted. The merger of two black holes creates ripples in space-time called gravitational waves, which travel outward at light speed and were first detected by LIGO in 2015, opening a new window for observing the universe. Black holes are not cosmic vacuum cleaners that suck in everything. Objects can orbit them safely just as planets orbit stars, but crossing the event horizon is a one-way journey into the unknown. Picture approaching a stellar mass black hole from a safe distance, where its gravity is strong but not yet overwhelming. And you see nothing at first, just a dark circle against the background stars, an absence where light should be. Closer in, you notice the stars behind the black hole appear distorted, their light bent by the intense gravity, creating a gravitational lens effect that warps the view. Crossing the event horizon would be unremarkable locally, no wall or barrier, but outside observers would see you slow down and freeze at the horizon, your image red-shifting and fading away as time dilation becomes extreme. From your perspective, you would fall inward, experiencing increasing tidal forces, and eventually being stretched and torn apart by the difference in gravity between your head and feet, a process gruesomely called spaghettification. Variable stars are stars whose brightness changes over time, either due to internal pulsations, eclipses by companion stars, or eruptions. And these variations can range from barely detectable to dramatic changes of hundreds of times in brightness. Some variable stars pulsate regularly like cosmic clocks, while others are unpredictable, erupting suddenly or dimming mysteriously. And studying their behavior helps astronomers understand stellar physics and measure cosmic distances. Cepheid variables are among the most important for astronomy, because they pulsate with periods that correlate precisely with their intrinsic luminosity, making them standard candles for measuring distances to faraway galaxies. By measuring a Cepheid's period, astronomers can determine its true brightness, and comparing that to how bright it appears tells us how far away it is, a technique that helped discover the universe is expanding. Cepheid variables pulsate because of instabilities in their outer layers, where helium ionization causes the star to expand and contract rhythmically, with periods ranging from days to months. When the outer layers compress, the star heats up and becomes brighter, and when they expand, the star cools and dims, creating a regular cycle that repeats as long as the star remains in this evolutionary phase. Delta Cephei, the star for which the class is named, pulsates every 5.4 days, varying in brightness by about 1 magnitude, and it is located about 890 light-years away in the constellation Cepheus. These stars are supergiants that have left the main sequence, and they are evolving rapidly through phases of instability before eventually becoming supernovae or shedding their outer layers. RR Lyrae variables are similar to Cepheids but less luminous and with shorter periods, typically less than 1 day. And they are older stars found in globular clusters and the galactic halo. These stars also serve as distance indicators, though they mark shorter distances than Cepheids, and their presence in globular clusters has helped astronomers determine the ages of these ancient stellar groups. The pulsation mechanism is similar to Cepheids, driven by helium ionization in the outer layers, and the regularity of their periods makes them reliable tools for mapping the structure of our galaxy. RR Lyrae variables are typically metal-poor, meaning they formed early in the galaxy's history, and studying them gives insights into the conditions of star formation billions of years ago. Eclipsing binaries are pairs of stars that orbit each other, and from our perspective, one star periodically passes in front of the other, causing regular dips in brightness that occur with clockwork precision. These systems are not intrinsically variable. The stars themselves shine steadily, but the geometry of their orbit creates apparent variability that depends on our viewing angle. Algol, the demon star in the constellation Perseus, is the most famous eclipsing binary, dimming noticeably every 2.9 days when a dimmer companion passes in front of the brighter primary star. Studying eclipsing binaries allows astronomers to measure stellar masses and radii directly, because the orbital mechanics and eclipse timing provide precise data about the system's physical properties. Novae are sudden eruptions in binary systems where a white dwarf is stealing material from a companion star, and when enough hydrogen accumulates on the white dwarf's surface, it ignites in a runaway fusion explosion. The nova brightens dramatically, sometimes by a factor of 100,000 or more, making previously invisible stars suddenly visible to the naked eye before they fade back to their original faintness over weeks or months. These explosions do not destroy the white dwarf, unlike supernovae, and the system can undergo multiple nova eruptions separated by decades or centuries as the white dwarf continues accreting material. Some novae are recurrent, erupting every few years or decades, and one famous example is T Coronae Borealis, which erupts roughly every 80 years and is currently expected to erupt again soon. Supernovae come in different types, with type Ia supernovae occurring in binary systems where a white dwarf accretes enough mass to exceed the Chandrasekhar limit, triggering a complete thermonuclear explosion that destroys the star. Type Ia supernovae are incredibly consistent in brightness, making them excellent standard candles for measuring cosmological distances, and observations of distant type Ia supernovae led to the discovery that the universe's expansion is accelerating. Core collapse supernovae, types 2, Ib and Ike, occur when massive stars exhaust their fuel, and these explosions are more variable in brightness but equally important for enriching the galaxy with heavy elements. The distinction between supernova types depends on what elements appear in their spectra, with type Ia showing no hydrogen, type 2 showing hydrogen, and types Ib and Ice showing helium or neither, depending on how much of the outer envelope was lost before explosion. Wolf-Rayet stars are massive stars that have lost their outer hydrogen envelopes through powerful stellar winds, exposing helium or carbon-oxygen cores that burn at extremely high temperatures. These stars have surface temperatures exceeding 30,000 Kelvin, sometimes reaching 200,000 Kelvin, and they appear blue or even ultraviolet white among the hottest stars known in the universe. The mass loss rates are extraordinary, with stellar winds blowing off material at thousands of kilometers per second. And Wolf-Rayet stars can lose several Earth masses of material every year through these winds. These stars are nearing the end of their lives and will explode as supernovae soon. And some might collapse directly into black holes, depending on how much mass they retain through the final stages. Carbon stars are cool giant stars with unusual chemistry where carbon is more abundant than oxygen. And this reverses the normal chemistry of stellar atmospheres, creating exotic molecules like carbon chains and dust grains. These stars appear deep red with a distinctive spectrum showing strong carbon features. And they are thought to be stars in late stages of evolution where carbon from the core has been dredged up to the surface. The atmospheres of carbon stars contain molecules like C2, Cn, and C3, which absorb light at specific wavelengths and give these stars their characteristic appearance when viewed through spectroscopes. Carbon stars are important for understanding how carbon is distributed throughout the galaxy, because their stellar winds carry carbon-rich dust into space, seeding the interstellar medium with material that might eventually form planets or life. Magnetas are neutron stars with magnetic fields a quadrillion times stronger than Earth's. And these fields are so intense they can distort the vacuum of space itself, creating strange quantum effects. When a magnetar's crust cracks under magnetic stress, it releases a burst of gamma rays, and one such burst from a magnetar 50,000 light-years away briefly affected Earth's upper atmosphere in 2004. These objects are extremely rare, with only about 30 known magnetars in the galaxy, and they fade relatively quickly, with their magnetic fields decaying over tens of thousands of years. Magnetars represent the extreme limit of magnetic field strength possible in the universe, and studying them helps physicists understand how matter and energy behave under conditions impossible to recreate in laboratories. Thorne-Jitkov objects are hypothetical hybrid stars, consisting of a neutron star that has spiraled into the core of a red supergiant, creating a star within a star, a bizarre configuration predicted by theory, but rarely, if ever, observed. If such objects exist, they would appear as red supergiants, but with unusual chemical signatures from nuclear reactions occurring around the neutron star at the center. One candidate, HV 2112 in the Small Magellanic Cloud, shows chemical anomalies that might indicate a Thorne-Jitkov object, though confirmation is difficult and the interpretation remains uncertain among astronomers. These exotic objects would be incredibly rare, forming only in very specific circumstances. But their existence would demonstrate that stellar evolution can produce configurations stranger than anything we typically imagine. Picture the universe as a vast laboratory where nature experiments with every possible configuration of matter and energy, creating stars of every conceivable type, from failed brown dwarfs to blazing blue supergiants. Among all these types, some pulsate like heartbeats, others erupt unpredictably, and still others spin hundreds of times per second, their surfaces moving at relativistic speeds. The diversity is beautiful and humbling, reminding us that our sun, steady and reliable as it is, represents just one note in a cosmic symphony of stellar types spanning the entire spectrum of possibility. We are fortunate to live in an era where telescopes and detectors can observe all these types, from the faintest brown dwarfs to the brightest supernovae, teaching us about the universe, one star at a time. Star formation begins in cold, dark molecular clouds, vast regions of gas and dust where temperatures hover just above absolute zero, and gravity slowly pulls the material together into denser clumps that will eventually become stars. These molecular clouds can be hundreds of light years across and contain enough material to form thousands or even millions of stars, though the process is slow, taking millions of years from the first gravitational stirrings to the ignition of fusion. The Orion Nebula is one of the closest and most studied star-forming regions, located about 1,350 light-years away, and it contains hundreds of young stars in various stages of formation, from protostars still embedded in their birth clouds to newly formed main-sequence stars. Other famous stellar nurseries include the Eagle Nebula, with its iconic pillars of creation, and the Carina Nebula, where massive stars illuminate vast clouds of gas and dust while triggering new generations of star formation. Molecular clouds are mostly hydrogen, with about 10% helium and traces of heavier elements. And the clouds are cold because they are shielded from starlight by dust grains that absorb radiation and prevent heating. Within these clouds, the densest regions begin to collapse under their own gravity. And as the material falls inward, it heats up through gravitational compression, slowly increasing in temperature and density. The collapsing region, called a protostar, is not yet hot enough to sustain fusion, but it glows in infrared light from the heat of collapse, visible to infrared telescopes, even though it remains hidden in visible light by surrounding dust. The protostar continues growing as more material falls onto it, and if it accumulates enough mass, eventually the core temperature reaches about 10 million Kelvin and hydrogen fusion ignites, marking the birth of a true star. The minimum mass required for hydrogen fusion is about 0.08 solar masses, roughly 80 times the mass of Jupiter, and objects below this threshold become brown dwarfs, never achieving true stellar status. There is no upper mass limit set by fusion physics, but the most massive stars ever observed have masses around 150 to 300 solar masses, and stars above this range become unstable, tearing themselves apart through their own radiation pressure. Most stars form in clusters or groups rather than in isolation, because the collapse of a molecular cloud typically fragments into multiple dense regions, each forming its own star or system of stars. Young star clusters, called open clusters, can contain hundreds or thousands of stars, all born from the same cloud within a few million years of each other, though most clusters eventually disperse as their stars drift apart over tens or hundreds of millions of years. Protostars go through several stages as they contract and heat up, and one dramatic phase is the T-Tauri stage, where the young star experiences violent variability, strong stellar winds, and powerful magnetic activity. T-Tauri stars are surrounded by protoplanetary disks of gas and dust, and within these disks, planets begin to form through the gradual accumulation of dust grains into larger and larger bodies. The disk material gradually accretes onto the star or is blown away by stellar winds, and within a few million years, the star settles onto the main sequence, where it will spend the majority of its life burning hydrogen steadily. By the time the star reaches the main sequence, any planets that will form have mostly finished assembling, though collisions and orbital rearrangements might continue for tens of millions of years afterward. Star formation is often triggered by external events such as supernova shockwaves or collisions between molecular clouds. And these disturbances compress the gas, increasing density and accelerating the onset of gravitational collapse. Massive stars that form within a cloud emit powerful ultraviolet radiation and stellar winds. And these energetic outputs can both trigger new star formation by compressing nearby gas, and also shut it down by dispersing the remaining cloud material. This feedback process regulates how many stars form in a given region, and it explains why star formation is self-limiting, with massive stars eventually destroying the clouds from which they formed. The interplay between star formation and destruction creates a cycle, where clouds form stars, stars blow away clouds, and the dispersed material eventually cools and recollects to form new clouds and new stars. The cosmic cycle of stellar birth and death has been operating for over 13 billion years, and each generation of stars enriches the interstellar medium with heavier elements, making subsequent generations more metal-rich. The first stars in the universe, called Population 3 stars, formed from pure hydrogen and helium with no heavy elements, and they were likely extremely massive and short-lived, dying in supernovae that seeded the universe with the first metals. No Population 3 stars have been definitively observed because they all died billions of years ago. But astronomers continue searching for evidence of these ancient stars in the most distant and oldest parts of the universe. The Sun is a Population 1 star, meaning it contains about 2% heavy elements. And this enrichment made possible the formation of rocky planets like Earth, which require elements heavier than hydrogen and helium. Every atom in your body was created inside a star, or in the explosion of a star. And this is not metaphor, but literal truth, the result of billions of years of stellar nucleosynthesis. The hydrogen in your body formed in the Big Bang, but the carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood, all were forged in stellar cores or supernova explosions. When a star dies and disperses its material, that enriched gas becomes part of new clouds, and new stars and planets form from the mixture, carrying forward the legacy of previous generations. You are made of stardust, assembled from atoms that cycled through multiple stars before the Sun formed, and this connection links you directly to the cosmic cycle of creation and destruction. The future of star formation depends on the availability of gas, and the universe contains vast reserves of hydrogen still available for making new stars, though the rate of star formation has been declining for billions of years. In the Milky Way, stars form at a rate of about 1 to 3 solar masses per year, which might seem fast but is actually slow compared to galaxies in the early universe, where star formation rates were tens or hundreds of times higher. Eventually, in trillions of years, the gas will be exhausted or dispersed, and star formation will cease, leaving the universe populated only by stars already formed and their remnants, a slow fade into darkness. But that lies in the unimaginably distant future. And for now, stars continue to be born, lighting the cosmos with new fires and continuing the cycle that has shaped the universe since the beginning. Picture a molecular cloud in the depths of space, dark and cold, barely visible except as a shadow against the background stars. And within that cloud, gravity begins its slow work, pulling material together into denser clumps. Over millions of years, these clumps grow, heat up, and eventually ignite. And newborn stars emerge from the darkness, their light illuminating the cloud from within, creating the glowing nebulae we see through telescopes. The cycle continues, from gas to stars to remnants to gas again. And each turn of the cycle takes billions of years, a process so slow and vast that human lifetimes capture only the briefest instant. Yet we can understand the cycle through observation and physics, and we can see our place within it, temporary inhabitants of a planet orbiting a star that will someday return its material to space, continuing the eternal cycle. We have traveled together through every major type of star in the universe, from the coolest brown dwarfs that barely glow in infrared to the hottest blue giants that burn with the light of millions of suns. Each type represents a different mass, temperature, and lifetime, and together they form the spectrum of stellar diversity that fills the cosmos, painting the universe with light across every wavelength. The stars we see in the night sky are not all the same, and now when you look up, you can recognize the red giants, the blue supergiants, the steady yellow dwarfs, each one a different kind of stellar fire burning across the void. This knowledge transforms the night sky from a random scattering of points into a comprehensible pattern, where each star has a story, a past, a present, and a future written in its color and brightness. Stars are not eternal, though many live far longer than human civilizations, and understanding their life cycles helps us appreciate the transient nature of all things in the universe. Our sun is middle-aged, with billions of years remaining before it swells into a red giant and ends its days as a white dwarf. And Earth's time as a habitable world is similarly finite, though measured in billions rather than millions of years. This perspective is both humbling and oddly comforting, because it reminds us that nothing is permanent, not stars, not planets, not even the galaxy itself. All things change and evolve over cosmic time. Yet within that change lies creation, as dying stars seed new generations. And the cycle continues, each ending also a beginning, each death also a birth. The diversity of stars reminds us that the universe is creative and experimental, trying every possible configuration of mass and energy, producing objects that range from familiar to utterly alien. Some stars pulse like heartbeats, others spin hundreds of times per second. Some are so large they would engulf multiple planets, while others are smaller than Earth, yet contain the mass of the Sun. This variety is beautiful, a testament to the richness of physical law, and it suggests that the universe is full of surprises, objects, and phenomena we have not yet discovered or imagined. Every new observation, every new telescope reveals more complexity, and the study of stars remains one of the most active and exciting fields in astronomy. Looking up at the night sky, you are seeing light that has traveled years, decades, centuries, or even millennia to reach your eyes. And that light carries information about stars that might have changed or even died in the time it took the light to cross space. When you see Betelgeuse glowing red in Orion, you are seeing light that left the star about 650 years ago. And the star as it exists right now remains unknown, visible only to observers 650 years in our future. This time delay means we see the universe as it was, not as it is. And looking deeper into space means looking farther back in time, until the most distant stars show us the universe as it appeared billions of years ago. Astronomy is the study of light and time, not just space. And every observation is also a journey into the past, witnessing the history of the cosmos written in starlight. Stars connect us to the universe in profound ways, and every element in your body except hydrogen was created inside a star that lived and died before the sun was born. You are made of stardust, literally, assembled from atoms forged in stellar cores and scattered into space by supernovae, eventually becoming part of the solar system and Earth. This connection is not abstract, but physical and direct. The carbon in your DNA, the calcium in your bones, the iron in your blood, all stellar products, all gifts from stars that died billions of years ago. Understanding this makes you part of the cosmic story, not separate from the universe, but woven into it. a temporary arrangement of atoms that once existed in stars and will someday return to space. The stars will outlive us, as they have outlived all previous generations, and they will continue shining long after our civilization has transformed or ended, patient fires burning in the dark. Red dwarfs will shine for trillions of years, long after the sun has died and Earth has become a cold, dark relic. And in that distant future, the universe will be darker, but not empty, still lit by the embers of the smallest stars. Some of those stars might host planets where life evolves intelligence, and those distant civilizations will look up at their own night skies and wonder about the stars, just as we do now. The cycle continues, consciousness arising and wondering, each generation of minds looking upward and asking the same eternal questions about origins, endings, and the nature of the cosmos. So, as this journey ends, take a moment to appreciate the stars, both those you can see with your eyes and those visible only to telescopes, from the faintest brown dwarfs to the brightest supergiants. Each one is a world unto itself, a sphere of fusion fire or a remnant of fusion's end. And collectively they form the visible structure of the universe, the lights that prevent the cosmos from being entirely dark. We are fortunate to live in an era when stars still shine abundantly, and when our technology allows us to study them in detail, understanding their natures and histories through the analysis of light. The night sky is a gift, a window into deep time and vast space, and it costs nothing to look up and wonder, connecting yourself to the cosmic story that surrounds and includes us all. Let your mind rest now, carrying with it images of stars in every color, red embers that burn for trillions of years, blue torches that blaze brilliantly and die young, yellow suns like ours that provide steady warmth. Picture the molecular clouds where new stars are born, the beautiful nebula where old stars shed their outer layers, and the exotic remnants where physics reaches its limits and breaks down. All of this is real, not fantasy, but actual physical objects scattered throughout the universe, and understanding them means understanding the cosmos, the stage upon which all existence plays out. Sleep well, and when you wake, remember that you are part of this story, made of stardust, living on a planet orbiting a yellow dwarf under a sky filled with countless stellar fires. The stars await your next glance, patient and eternal from our perspective, and they will still be there tomorrow night and the night after, slowly moving through their ancient cycles, burning quietly in the dark. They have witnessed everything on Earth, from the first life to the present moment, and they will witness whatever comes next, indifferent observers of a planet orbiting an ordinary star. There is comfort in their constancy, knowing that no matter what happens in human affairs, the stars will continue shining, the universe will continue evolving, and the cosmic cycle will continue turning. We are small in space and time, but we are also privileged, conscious beings who can look outward and understand, connecting our brief lives to the eternal dance of stars. The Drowsy Astronaut thanks you for joining this journey through the stellar types, and I hope you found wonder in the diversity and beauty of stars, from the smallest to the largest, the dimmest to the brightest. Sleep well tonight, and let your dreams carry you among the stars, drifting through nebulae, orbiting blue giants, watching red dwarfs glow softly in the eternal dark. The cosmos is vast, but it is knowable, and each night the stars offer themselves for study, for wonder, and for the quiet contemplation that helps us understand our place in everything. Good night, and may the starlight find you wherever you are, connecting you to the universe, to the past, to the future, and to the eternal cycle of stellar birth and death that shapes all things.